Welcome back to the Contractor School. Remember to take good notes. We're still in Ohm's Law. And moving on to this question, use Ohm's Law to calculate the total resistance of a circuit that has a resistive load of one single appliance. The appliance has a nameplate of, 13 amps, that's a given, and a load of 1.44 kilowatts, that's another given, but the operating source voltage is unknown. That's interesting. Okay, well, if we look at the answers, I always like to look at the answers. I think that makes sense because it tells me what the question is, right? Ohms. I'm looking for ohms, and I'm given amps, and I'm given watts, right? So this is kind of a very unique question. Looking at our wheel, which one resistance we know is over here, right? And I don't know the voltage. The question even said there wasn't a voltage, but I was given power. That was the 1.44, okay? And then I was also given the ampacity, was I not? So if I know the power and the ampacity, right? The power down here and the ampacity, well, I can figure out the resistance, right? So let's just go ahead and draw this one in our notes, okay? If I have a circuit and I don't know the voltage, so I'm just going to go and draw a source voltage here, even though I don't know what it is, right? And then I got a resistive load out here, okay? And then I do know the power. It said it was 1.44 kilowatts, right? And the resistive load itself, we don't know, but we do know the ampacity flowing through it. So if we know the ampacity, right, 13 amperes, right, 13 amperes, and let's draw this one also in our notes. If we know that there's 13 amps flowing through this circuit, right, couldn't we figure out this load right here, R sub T, right, or R sub T for total resistance, or just R, right, for resistance? Well, sure, that was the formula. R is equal to, let's take one more look here, make sure we got it down. And once again, this formula will be provided. Power divided by I squared, right? We don't know the voltage, but we do know the power and the ampacity, right? If we know the power and the ampacity, then we could just plug that in there, okay? So wouldn't it be R is equal to the power divided by I squared. Now, there's a couple of odd things that maybe you're not comfortable with, and let's make sure we understand. First of all, power in watts, no problem, right? So we'll just write it up there. But as far as I squared, isn't that simply just I times I? Well, sure, right? I times I, right? I squared, right? E squared, P squared, whatever, they use squared just means that value times itself. So I, and then another I, right? Because it's squared. If it was cubed, it'd be different, right? But we don't use that. I times I is I squared, okay? Then we just go ahead and put our numbers in there. Now, power, it's in kilo here. I want to get it out of kilo, right? So if I want to get it out of kilo, wouldn't I go 1.44? And if I want to get it out of kilo, wouldn't I go 3 places to the right? 1, 2, 3, and then add a 0, right? So wouldn't it be 140, I'm sorry, 1440 watts, right? So kilowatts to watts. Pretty simple. Move over 3 decimal places, 1, 2, 3 to the right, and you have watts from kilowatts. Okay, pretty simple. Now, so put it up here, 1440 watts. And then the ampacity in this case was 13 amps. You can see it's drawn in here, right? So over here on the up the right, that's one of the givens, right? That's one of the givens right there, right? And the other given was down here, right? So I knew resistance and I knew power, so I can figure out what R is, right? I can figure out what R is, okay? Power divided by I squared. So power, once again, was given in the question, as was ampacity, 13 amps times 13 amps, right? And then we just simplify here using our calculator. We go ahead and simplify. And let's pull mine up. You pull up yours. 13 times 13 is 169. So let's write that in there. Our 169 on the bottom. On the top, we still got 1440, right? And then we just simplify. Okay, so It's very important to always write this in your notes whenever you get an answer right. Make sure you put a box around it. So let's use our calculator one more time. 1440 divided by 169. We'll get the correct answer, 8.52. 8.52. And then the units are in, what are the units here? Not amps, not watts, not volts, but ohms, right? And let's go ahead and put a box around it. That's the correct answer. Okay, let's go ahead and knock off one more question here on Ohm's law. Okay. Let's see, where did it go? This one. Let's go ahead and do this one here. Calculate the electric heater load. Okay. We can draw this in there, right? It's always best to draw the circuit. We're looking for power this time. Not the last one here, we were looking for ohms, right? We're looking for the resistance of the load. This time we're looking for power. It's just real simple stuff, little circuit analysis here. Pretty easy to do these things. So we're looking for power, and this time we're given ampacity and we're given resistance, right? So there's a formula for that. Power is equal to I squared times R. They're right there on your on the screen, as well in your formula wheel. Wouldn't it be formula number 10 over here? Sure, formula number 10. I squared times R gives us power, right? Once again, go to this section of the wheel for power. Why? Because all the answers are in watts, so we know we're looking for power. Okay, we know we're looking for power. And we can't use this one because it has E, that's voltage. We don't have the voltage, not given in the question. But what is given in the question is ampacity and resistance, so we know we need number 10. Okay, it's very important to go to the right section of the wheel, in this case power, choose the appropriate one out of the three formulas in that section of the pie, and then knock this thing out. Okay, so let's go ahead and put this one in our notes. Right, in this case we have 6 amps and 20 ohms. Okay, so we'll just draw it, 6 amps and 20 ohms in our notes. We draw our circuit. With a 20 ohm load, right? We got 6 amps flowing through it, and then we can figure out other things, right? If we know these two variables, we know ampacity here is 6 amps, and we know the resistance is 20 ohms, we could even figure out the voltage there, but it didn't ask for voltage. We could figure out the voltage, but it wasn't asking for voltage, it was asking for power, right? So then we need power is equal to I squared times R, right? I times R, right? And we just go ahead and knock this thing out and finish her up. 6 amps times 6 amps times the resistance of 20 ohms, and then we need our calculator, right? So let's go and pull up our calculator. So I'm gonna get this out of the way a little bit here. 6 times 6 times 20 is 720. So let's go ahead and put down 720, and we're solving for power. So the units of power is what? Well, easy stuff here, right? Units of power is watts, right? So let's put that in there, put a box around it. We're good to go. Solved another Ohm's law question. Okay. So kind of in review, right? The formula was needed, right? One unknown, power in this case, 2 givens. We looked for resistance, was an unknown. Power and ampacity was given. Definitely on the test, definitely without question, you're going to have to solve for I is equal to P over E. That one's always on the exam, always, always, always. So just choose the right section of the wheel, I, E, P, or R, and then grab the formula and use it, okay? You don't have to memorize this wheel, it'll be given to you. Okay, and if it's not given to you, you need to ask for it. Okay, you got to have this wheel to solve these things. Okay, so let's go ahead and move on in this lecture here. I want to go into service loads. Service loads going to take a little while to solve this thing. Now, I would preface this discussion with when you see a service load calculation and all this kind of detail here, electric heat, dishwasher, all this stuff, I would just skip it, come back to it later. These ones generally take 5, 10, 15, or even 20 minutes to solve, and they could really take you down the rabbit hole that you don't want to go to. So I would strongly recommend, when you see services, questions that look tricky, or even range load questions that look tricky, leave them alone, come back to them later. They're usually going to gobble up a lot of your time, and since this is a timed exam, that could be a bit of a problem. So let's go and open up our code books. We'll go to Annex D, first of all, in our code books. I'm going to go ahead and search for it here. You guys could probably get there quicker than me if you have tabs. You should have tabs in your code book by now, and your code book should already be highlighted. And the reason I say that is, I prefaced this lecture with all of these things written in our workbook, right? I'm on page 6 of our workbook here as well. The Annex D is listed here. Of course, it's listed. Why? It's always used for the exam. But so is Annex C. So is Chapter 9, Table 8, and all these other tables as well. So these things should already be highlighted in your book. So let's try to move on a little bit quicker. If you're not highlighted, we'll try to highlight and pay attention at the same time and take good notes. Take good notes here, okay? So Annex D. Annex D. Annex D examples. The first couple examples are pretty good. Maybe even the first 3 or 4 are pretty good, but then it gets pretty lengthy in there. I wouldn't spend too much time beyond these first couple of examples when talking about service loads, okay? So example D1A, one family dwelling, and you can kind of see how they do this thing here. That's a 1,500 square foot home times 3, gives you the load for the lights, right? And then you got small appliance and you got laundry. All these things need to be added up, okay? And you can see how they do it here in the code book, okay? That's a pretty good example right there. That's the math for example D1A, one family dwelling, there at the top of the page. Looks like page 791 on my book, the NEC 2017. Okay, so general lighting, small appliance, laundry, group together, derated, then you add your range and your dryer, and you get your net. Okay, so that is the standard that we're going to use. That is what we call the standard method. On the next page, there's one more example, by the way, of one family dwelling. There's 2 examples total, and that's good that they have 2 different examples, and that's great. You should go through them both so you understand them both. But example 2 now is a little unique because it's optional calculation method. And that probably will not show up on your exam, but if it does, here's the math on how to do it. It's pretty simple. Just add everything up and derate. Okay, that's actually easier than the standard method. It generally comes up with a smaller number, actually. Okay, so going back to our standard method, right, on page 791, and this little procedure here, you should highlight and go through later on your own time, because it should make sense after this lecture. Okay, it should. If it doesn't make sense after this lecture, you need to call the school and get your questions answered, because this math does need to make sense. Okay, so let's go ahead and solve the question we have on the board. Okay, now the question we have on the board it's a full calculation. It actually constitutes quite a bit of work. So like I said, this will probably take me 10 or 15 minutes to solve, and it's going to take a little bit of paper. So let's be patient here. According to National Electrical Code, and referring to Annex D1 for the standard method to apply any derating principles, what would be the minimum size service entrance conductor and capacity given the following details? Oh boy, it's a single family dwelling, and here's all this stuff, right? The first thing I look down, okay, it's a dwelling, that's great. I know what the numbers are for that and what tables I need. I can see it's a 3-phase, I mean it's a 3-wire service, right, single phase. And then this is the first detail that's important. 3,200 square feet, okay? 3,200 square feet. Well, there is a table that we need to look up real quick, and this isn't a highlighting class. I expect most things, these things to already be highlighted, but let me go ahead and open it up just so we can kind of take a quick peek, make sure we're on the same page, okay? So I'm going to Article 220. So if you can kind of keep up with me, that would be great. But there's a table here, okay? And it should already be highlighted once again. If it's not, come on, box it around. I won't tell you this too many more times. Box all the way around, put just like a line on the top, then go ahead and put a line on the side, all the way around, and put a box around it, okay? Now, if you notice, in here is a dwelling, and the multiplier in volt amperes for the dwelling is a 3 volt amperes per square foot. Okay. The other things you may want to highlight since we're here, because they do ask, the lighting for a church is a multiplier of 1. The lighting for a bank is 3.5. Right. Those you should highlight. Other things that show up on occasion is a loft. Right. Multiplier for a loft right there. Multiplier of 2. Okay. Office always shows up. Lighting for an office building, 3.5. Okay, and then coming down to the bottom here, assembly halls. That's asked every once in a while, and it's a 1 volt ampere per square foot. So regardless of the occupancy, you can come to this particular table and find out your volt amperes per square foot based on the square footage of the occupancy. Okay, so in this case, it's a dwelling, and we just saw that it was 3, right? So we need to write this in our notes and tally this thing up. Okay, so let's go ahead and start taking good notes now. Don't forget to write this down, because this is how to do a complete service load. Okay, so let's go ahead and write it down in our notes and make sure we get it in there. I'm gonna have to clear this page. So the first thing was the lighting based on the floor. Okay, so I'm going to put a 1 here, right? And the first thing are my lights, right? So my lighting is in this case for this particular question was 3,200, right? So wouldn't it be 3,200 square feet times 3 volt amperes per square feet? Okay, that's where the square feet are going to cancel, right? Leaving me with volt amperes. So let's go ahead and get our calculator out. Make sure we get this thing down here. 3,200 times 3 is equal to 9,600. So let's just write that in there. 9,600 volt amperes. Okay, so write that in your notes. 9,600 volt amperes. 9,600. Okay, next thing is our small appliance, right? Small appliance, if it's a dwelling, is required. Small appliance, right, is 1,500 watts, but you need 2 circuits, so times 2. So that one's going to be equal to 3,000 volt amperes, right? That's for the small appliance. It is a requirement in a dwelling. Number 3, the laundry, right? 1,500 watts again for that circuit, but there's only 1 of them, right? So of course 1,500 here on our tally. Okay, now these need to, I'm going to put a note over here, these need to be derated together, right? These are what we call our required circuits by the NEC, so let's write that in there. Required by the NEC. Those are required circuits by the NEC, and they need to be derated together. So how do we do that? Well, the way we do that is we tally them up, right? If we just keep things square here, should be able to put it 0, right? This is another 0, right? 6, 0, and 5 is an 11, carry a 1, right? 10, 11, 12, 13, 14. So I got 14,100. Okay, now this is before derating. Now on the back of that annex, it shows you how to do it, but I'm going to show you here live so you can get it in your notes and get an understanding here. So this 14,100 volt amperes is before derating, right? So what we need to do is derate. Now the way we do that is to subtract 3,000, because we're going to take this first 3,000 and I'm going to put over here at 100%, right? And it says that in Article 220.12 as well. And go ahead and read that later. Okay, we're going to take this portion, right? This is our not what we call our non-derated portion. I'm going to put that in here. Non-derated portion. This is our non-derated portion. This this 3,000, okay? We need to, the NEC says that you cannot derate 3,000 of it, but you can derate the rest or the remainder. So we need to subtract the 2, and we subtract the 2 when we get 11,100 volt amps, right? And this portion needs to be derated. This portion needs to be derated, right? This is what we're allowed to derate according to the NEC by 35%. So it's multiply by 0.35, right? Right. This is of course 35%, right? According to the NEC, that's what we're allowed to do, right? And like I said, it's in Article 22012 there. But we take the first portion at 100%. We derate the remainder, the 11,100, at 35%, right? So we multiply these two out, right? We get, let's go and do it on a calculator. That'll help slow me down anyway, right? So we got 11100 times 0.35, and we get this here 3885. Now this 3885 volt amperes, this is our derated portion, right? So when we need to get the non-derated portion from up here and add it to our derated portion down here, sure. So we got to get the 3,000 and add it to the 3885, right? So if we get 3,000 plus our 3885, that comes out to 6,885 volt amperes. Now those are just for our, and we should put that in there, right? This is for our lights, our small appliance circuits, times there's 2 of them, right? And our laundry, right? That it's for all 3 of those. I'm going to put like a little line around that, right? So that's in essence the first step, right? That's kind of like step number 1, right? Is to get these, what we called earlier, required circuits by the NEC, right? Required circuits by the NEC, right? Or lighting, small appliance, and laundry, right? And when we add them up, 9,600 volt amperes, right? Because it's 3 volt amperes per square foot. Get the 9,600. Add up our small appliance of 3,000. Add up our 1,500 for our laundry. End up with 14,100. Now that's before derating. That's before derating. We got to derate this thing. Subtract 3,000 because we need to take that 100%. When we subtract 3,000 for 14,100, we get 11,100. Multiply by 35% to get 3885. That's our derated portion. Then we add what I'm going to put here in an oval, right? That's our derated portion. And then up here, our non-derated, I'm going to put in a rectangle, right? And so don't we need to add those 2 numbers together? Our non-derated and our derated portion. That's what we did down here. 3,000 plus 3885 equals 6885. Now that's, like I said, step number 1. Okay, so we kind of need to clear the page here and write that down as step number 1. So I'm going to start a new page here. You may need to continue on yours as well, or I'll flip the page as well. But let's go ahead and continue. So step 1, right? And so I'm just going to put a 1 here, right? And this was for our lights, our small appliance, and our laundry, right? That gave us 6,885 volt amperes. Okay, that's just step number 1. Okay, now we got to continue here because there's more stuff. And you say, well, wow, I mean, what stuff? Well, wasn't there a range? Well, sure, there was a range. Just go back and look, right? And sure enough, there's a range. 8,000 watts. Now that's a good thing. It's only 8,000 watts, because if it's over 12,000, it gets ugly. Like 14,000, 18,000, 20,000. Those you have to derate, and it just makes kind of a mess. But this one, the table's quite easy. So let's go ahead and go to the table. for ranges. Table 22055. Table 22055 in your code book, if you would, please. It's a pretty big table. Always on the exam. I'll guarantee it's on there. Now we got an 8,000 watt range. So wouldn't we need to be in column B here? Because this column here is 3,500 watts, right? 3,500 watts through 8,750 watts, right? So we need column B here because we got 8,000 watt range, right? And this gives us a percentage multiplier. If it's 3,000 watts, for example, which will come up here in a minute, that would be over here, okay? But this is not 3,000. This is 8,000, so we'd be here. Now the other thing is that if it's 9, 10, 11, or 12,000, or even more than 12,000, we'd be needing to use column C, but that's not the case. Here we're on column B in this case, and we only got one range, right? So since we only have one range, we slide on over, and we should see that 80%, right? That 80% right there. Now that's in percent, so you might want to highlight percent over here, because these two columns, both these columns, are in percent. And then over here, you might want to highlight kW because these are in watts on this side, and these are in percentage. So highlight or circling is fine too, right? Get a big old fat circle around the percent and then around the kW. So 80% in this case. Why? One appliance, and it's in the range of 3,500 to 8,750. So 8.8. Okay, so let's work with that. Let's go back to our question. The range for 8,000 watts. Okay, so in our notepad, right? In our notepad, wouldn't we go ahead and put for the range of 8,000 watts? Oops, need another zero there. Watts, and then wouldn't we do multiply by 0.8? Right, that's what we got from the table, and that's pretty simple math, right? That's 6,400 volt amperes. Okay. Make sure you get that in your notes, right? Let's go and double check. Slow me down, right? 8,000 times 0.8, 6,400, sure enough. Okay, good. So the next thing listed after the range, I believe, was a dryer. And sure enough, a dryer 5,300 watts. Now there's a code reference on that, 22054. And let's just turn there real quick, because that one is on the exam, and they like using the table associated with that one for actually the kitchen equipment's on there too, but then let's see where we're at. 22054 is where we're going. There it is, electric clothes dryers. They like using this table. They like coming down over here, and you have to use these notes down over here to solve. But in this case, we really don't need the table. We just need to know the article over here, right? 22054, that's 5,000 watts, or the nameplate rating, whichever is larger. I do want you to highlight that. 22054, that's what it says. So in our case, 5,300 is bigger than 5,000, so we use 5,300, okay? So back to the question. For the clothes dryer 5,300, we just put in our notes 5,300, okay? So number 3, the dryer. 5,300 watts is simply in our notes 5,300, and that's all there's to that. Now if we needed the table, then we use the table, but we didn't in this case. Okay, now the next thing is a dishwasher, 1,600 watts. We just put that one straight away. There's no D rating for that one. Okay, so number 4, dish washer, 1,600. Keep everything nice and square if you can. Make sure it's kind of pretty, because it takes a while to get these done, and you don't want to have a mess here. This is 1,600. This is 1,600. There's a 6 right there. Okay. Then the last thing here is the heat, right? So let's take a look. Heat was 20,000. So let's put that in there as well. Number 5 is your heating. Right, and add it in there, 40,000. No, I'm sorry, 20,000. Come on, Julian. 20,000 volt amperes. Okay. Let's get it in there. Heating. Is 20,000. volt amperes. Okay. Now, we need to tally this thing up, don't we? We need to tally this thing up and add it all up, okay? And if we use our calculator, we multiply, we add everything. We got to add all of these up on our calculator. I'm just going to save us a bit of time here. And after they're all added, we land up with 40,185 volt amperes. So write that in your notes. Try to catch up here. So that's our total power, right? That's our total load in volt amperes or watts, right? So if that's the total load or total power, right? Well, the question was asking for amperes, wasn't it? The question was asking for amperes, right? So if the question was asking for amperes over here, right, and we know the total power, can't we come back over here to the wheel, right, and say, okay, if I'm looking for amperes, I need power divided by the voltage. Well, home operates on 12240, right? If we know the total power and we know the voltage of the service, we could calculate the ampacity on the service and therefore the conductors if required. Okay, so in this case, let's go ahead and go to our notepad. I is equal to P divided by E, right? And the power we just calculated here, right there it is, 40,185 volt amps divided by 240 volts on a single phase service, right? And we multiply those, we divide those two out. 40,000, it's going to pull up our calculator. I'll pull up mine, you pull up yours. Get this thing done here. 40,185 divided by 240, and then we got 167 amps. I strongly recommend you put a box around it and memorize that answer. And if you see this question in any form with those numbers, which you probably will, that will be the correct answer. Okay, I'm going to re-emphasize here that once again the workbook, right, going back to page 6, has the form of the wheel, but this next question on page number 7 of the workbook is also a service load, and it goes through exactly the same kind of math. It's just based on the square footage of the house, 3,000 square feet plus, and then there's a garage which you don't count because you don't live in the garage, and it's not heated, right? It's not livable space, but this 1,000 unfinished for habitable space you would add, so that'd be 3,000 plus 1,000 for 4,000 square feet, right? So down over here, if we're looking at the math, right, wouldn't it be 4,000 square feet times 3, right? That gives us 12,000. That gives us 12,000, and then we got to add 3,000 for the small appliance, 1,500 for the laundry, and that gives us the 16,500. Right? Subtract 3,000. That's our non-derated portion, giving us the 13,500. Multiplied by 35% gives us 4,725, and that needs to be added back to our non-derated portion of 3,000, and you get the total load for just the required circuits by the NEC of 7725 volt amperes. And notice there's no range, there's no dishwasher, there's no clothes dryer and heating and all that. This was just based on the square footage. Okay, so once again, this little cutout here, cut and paste, was actually from the 2014, but whether you're using 2014, 2017, math's the same, hasn't changed a bit. Okay, surface loads, once again, a little bit on the tricky side, but we'll go over a couple more examples and make sure we got it in this lecture. So I appreciate your time. Thank you very much.